Okay. Bring that closer, I guess. Yeah, with all the previous speakers, though, I don't want to get like weird diseases and shit. No. So.
After last night's party, it's probably a little bit too late for that.
Yeah, good point. Well, I mean, it's all itchy.
Hey, you know, there's some drugs in Tijuana you can buy that actually will cure most of that. Get rid of the rash, too.
Well, I'll cancel my flight tomorrow and go down.
Okay, good.
Best talk ever!
All right, so Tom St. Denis is up here to talk to you now, and he has actually, usually we're used to authors that are a bit full of themselves, so kind of used to seeing people that have bios that are rather large, but Tom takes the cake in the relationship between his bio and the entire description of his talk. What is it, 5 words to talk, but I guess that's what he's going to spend the next 50 minutes discussing, explaining to you exactly what he means by elliptical curve cryptography, redux, I can't even say it. It's late, I'm tired. But Tom, everyone, big round of applause for him.
All right, so I'm Tom St. Denis, obviously. The talk is elliptic curve cryptography redux. So it's kind of a survey talk on ECC. I won't go too in depth. It's kind of light, enjoyable, whatever. I'm pretty much one of the sole authors of the series of libtom projects. So if you Google for libtomcrypt, you'll pretty much see what I'm about. Anyways. Quick disclaimer, because I had to do this earlier. I work for AMD. I don't represent them when I'm doing this. So don't go to them saying some weird guy went on stage and all that stuff. I'll be talking about some patents as well, but I'm not an attorney, so don't quote me. I just did a quick, U.S. patent search. That's about it. So take everything with kind of a grain of salt. This is my second Toorcon talk. Love the scene. It's cool. Basically, I spend my time dividing it between crypto, doing research and studying and reading any type of paper I get my hands on, development stuff, libtomcrypt, giving talks like this one, and authoring books. So I have my first book here, if you guys want to see it after the talk. And I'll have another book coming out in about November, so you should all buy it. Never worked for Advia, but that's kind of a Dan joke. Author of the libtom projects. I have a new website, so anyone who's known about my projects before, they were hosted at libtomcrypt.org. Dan forgot to re-register that, so there's now a squatter sitting on libtomcrypt.org. I have libtomcrypt.com now. I have briefly been dragged into the One Laptop Per Child project, securing their bias so they can do updates and not get completely pwned. But I'm not a core member of that project, so I'm just kind of, tagging along. Books, and of course I'm everything else. So for those who don't know, I came here with an EFF hat, and it's sunny in San Diego, so you need a hat. Dan borrowed it and managed to lose it, and it's kind of a weird, funny story. But anyways, I just put that up to embarrass him a bit. Okay, so let's get into the actual talk. Okay, so we're going to be looking at elliptic curve cryptography. So I'm assuming a lot of people here probably know about RSA, that type of asymmetric crypto. You know about things like AES, SHA-1, SHA-256, all that stuff. Very few people actually really understand what elliptic curve crypto means, specifically because it deals with a lot of weird algebra that for new people, like when I started going into it, it's really awkward and just horrible to think about. So I'll talk about that. We'll talk about why they're useful. So why do we even want to look at this if we already have RSA? We're looking into how we do encryption with this. So this is asymmetric encryption, public key encryption. How do we do signatures with them? What standards are out there that cover each? What type of curves do we have? And you probably won't know what a curve means at this point, but there are standard curves as well we'll be using. And I'll briefly touch on patents, copyrights, and all that other jazz, very briefly. And then finally, I'll end the talk discussing a cool algorithm that I developed a couple months ago. Gets really cool performance for ECC work. And this is not a libtomcrypt talk, unlike last year. So essentially, an elliptic curve is defined by the root polynomial. So the basic form, for those who can see it, y squared equals x cubed plus ax plus b. And then there's a more generalized form, the Weierstrass form. And from that, you can pretty much describe any elliptic curve you want to look at, not just crypto-related ones. A point is a pair of x, y that satisfies that equation. Pretty simple. The order of a curve is the number of pairs that satisfy the equation. And that comes into particular use when we're elliptic curves defined over finite fields. So we're not going to be dealing with real numbers or rationals or whatever. We're going to be dealing with, say, arithmetic modulo a prime, for example. So the gist of elliptic curves, that's what it looks like. These are two different forms over the reals. Pretty simple objects. So all those little red parts are points. Yay. So when we're getting into elliptic curve crypto, we have to define two primitive operations that we can use to work with points on a curve. So all our operations are being done with points, whereas in something like RSA or typical Diffie-Hellman, we're dealing only with integers. So that's kind of where the first step into weirdness begins. The two operations we're going to be looking at are point addition and point doubling. And from that, we can define elliptic curve crypto. So point addition is where you have 2 points and you want to add them together. This operation is completed by finding a line through the 2 points and find out where it intersects the curve. Point doubling is simply taking the tangent of the point. So I have pretty pictures to show this off. So this is point addition. So we're going to be adding P to Q, and we get R as a result. When you actually complete the point addition, you actually use the negative value of R. So it'll be the R that's below the x-axis. And the reason you do that is if you added Q to R, you would get P back, which isn't really a useful operation. You want to get a different result from that. And then point doubling, here's doubling Q to get P. So quite simply, it's just the tangent to the curve and where it hits. Really simple. So why do we care about addition and point doubling? It seems like a really weird operation to do. Well, from this, we can define point multiplication. And from that, we can get Diffie-Hellman DSA. So point multiplication is simply the practice of adding a point to itself multiple times. In this notation here, you'll see there's uppercase variables and lowercase variables. The uppercase variables will be points. So G is a point on the curve. It's an XY pair. Whereas K is a scalar, an integer, 5, 7, whatever. So when we say K, we're doing a point multiplication. So in this case, we're adding G to itself K times. From this, we can construct any point multiplication. So for example, if we wanted to find the value of 3G, we would double G and add G to it. If we wanted 5G, we'd do 2 doublings and an add, so on and so forth, like we do exponentiation with RSA. And in fact, a lot of the algorithms we use to do fast exponentiation, so RSA and Diffie-Hellman, you can take those and map them onto ECC pretty well. So now we have a trapdoor. If I give you the value of y, which is kg, and you know g but not k, finding k is hard. And this is the trapdoor we're going to be taking advantage of. It's similar to the discrete logarithm trapdoor. So you have y equals g to the power of x mod p. So I'm pretty sure you guys are familiar with that particular trapdoor, right? Okay, so from this we can start Diffie-Hellman key sharing. Alice has a public key, which is uppercase A times equal to AG. Bob has a public key, which is uppercase B. In this case, G is a publicly known base point that everyone starts from. So these are parts of standards that I'll get into briefly. From these two public values, though, they can share a key or share a point that no one else can compute, which is simply lowercase a, uppercase b, which is equal to abg. Or on the other flip side, you'll have lowercase b, uppercase a, which is bag. And since this is a group operation, abg and bag are the same point. And now they have a shared secret. Usually what will happen from this is you'll take the x coordinate and ignore the y and hash it and use that as a shared secret. You don't use the y value because if you looked at the graph earlier, there's only 2 values of y for any given value of x. So there's only 1 bit of entropy in it. It's not very useful to use it. It doesn't really add to the security of anything. So why are you, did I go too far? No, okay. Why is ECC in any way useful? It seems like kind of interesting math, but why would you be doing this? Well, it turns out ECC parameters can be a lot smaller than RSA parameters for a given level of security. In RSA, we can use algorithms like the generalized number field sieve to factor in a sub-exponential amount of time. Whereas in ECC, you don't have that advantage in attacking it. So it's fully exponential. So if you say you want 80 bits of security, with RSA you have to use 1,000-bit numbers. Whereas in ECC, you only have to use 160-bit numbers. We're going to be using less memory to do this, obviously, because the numbers are smaller. And there's various other tricks to compress it too. So there's point compression on public keys, but that's not important. You transmit less data, which is important. So a brief example of that would be ECDSA signature with 80 bits of security is 48 bytes with ECC, or it's 128 bytes with RSA. So you're already less than half the size. And you also get a lot of speed out of this. Since you're dealing with small numbers and there's tons of fast algorithms, I'll be presenting or talking about briefly, you can get ECC crypto on small devices. So anyone here ever work with an ARM, PowerPC, MIPS, whatever? Of course. So, of course, Greg. So a lot of companies that I've had dealing with, but I won't go into public stuff, but they just assume that if we can't do it, we'll do it insecurely. So we'll use 512-bit RSA or 300-bit RSA, and the average person will never look at that. And of course, people like, for example, in the back there, are the people who will look at that. So we can use ECC, use small numbers, but actually have real security, and we can fit them on stupid devices like Bluetooth mice or Bluetooth keyboards or Game Boys or whatever. We can also sign with it. So I briefly mentioned Diffie-Hellman, but we can also sign with it. Keep that in mind as the talk progresses. So stop for a second. Things I've learned at Toorcon so far. Headwear and Dan is a bad idea. And then, yeah, some stuff about the dance. You can see the slides later. Okay, let's get back into encryption here. What happens at Toorcon stays at Toorcon. Given Bob's public key, BG, we can encrypt. And we don't have to have, we don't have to know each other ahead of time to do this encryption. So it's not just a shared secret like Alice and Bob who know each other already, but if I have your public key, I can send something to you if you've never met me. And this is how you do it. Essentially, you just make up a random key, and that's where you're going to be sending to Bob. So you pick a random value of R, and I kind of stressed random. It's very important. A lot of Diffie-Hellman, straight-up Diffie-Hellman systems have been broken because they use things like the RAND function to get this random parameter. And anyone here should know that RAND is not exactly what you'd call a cryptographic random number generator. We take the point RBG, hash the X value, and use that as either a symmetric key or we can XOR it against the symmetric key that we want to choose. The payload. We send the ciphertext in RG to Bob. RG is effectively just a public key at this point. It would be what you would have in the first place if you knew each other ahead of time. On the other side, he then computes BRG from RG you gave him, recovers the symmetric key, and can decrypt the ciphertext. Yay! Signatures. So the first thing I say about signatures is follow standards. When I first implemented this stuff in my libtomcrypt library, I didn't really know about ECDSA because I'm not really a big fan of ANSI standards. They kind of annoy me. So I went off and implemented my own DSA variant, which was, it looked all nice, it worked and everything, and it was completely insecure. So I'm here to tell you, do ECDSA properly. X963 is the ANSI standard that covers it. I think it's finished now, but when I read it, it was a draft, so it's kind of, a work in progress. But the algorithms in it are pretty easy to implement. It's just a pretty much standard straight-up DSA. We'll see it in a second. And it's actually what NIST is specifying for EC signatures. So let's get with the signature here. We say we have a public key A and the private key A, lowercase a, and then times G, whatever. And we assign a message, MSG. So we'll hash it, get the parameter E, which is just an integer at this point, choose a random K, compute T equals KG, and then from this we'll get the R parameter of the DSA signature, which is just the X coordinate of our random point order of the curve. Right, 1 second. And then from that, after that, we'll get the S parameter, which is just, I don't know if it's really important that I read it out loud, but you get the S parameter from the random K you chose and their private key and the hash, and you send off to the user R and S. So R and S are integers about the size of the curve. So if you're talking about 192-bit ECC, these are 192-bit parameters. So your entire signature is 384 bits. It has 80 bits of, at that point,